Going to talk about thermal expansion. So we're going to start with linear expansion. Let's just get up here. Imagine you have a metal rod and you heat it, and the size of the rod increases. So we're going to call that linear expansion. We're only concerned right now about the length increase. We'll talk about area and volume in a second. So L subscript 0, L naught, is the initial length of the rod. Whoops, initial length. This is the temperature change. So how much you change the temperature of the rod. And then alpha is called the coefficient of linear expansion. Now from this, a change in length, okay, that's how much the rod grows, is given in meters. This is in meters. This is usually given in degrees Celsius. Now you might be saying, wait, I thought we were supposed to use Kelvin. Turns out, if you're talking about temperature changes, the increment size of the Celsius scale and the Kelvin scale are the same. So a 1 degree Celsius increment is the same as 1 Kelvin increment. And so that's not true if we're just talking about temperature, right? 30 degrees Celsius is not 30 Kelvin. But a change of 30 degrees Celsius is equal to a change of 30 Kelvin. So that's why we could use either units of 1 over degrees Celsius or 1 over Kelvin for this coefficient alpha. All right. Now, sometimes this is rewritten as L prime is the total length. Obviously, the total length should be the original length plus the change, and then you can factor out the original length. So those are the two common ways to write that. For an area expansion, and I've got a visual in just a second on the other board to help you visualize this, there's a factor of 2. I like to think about it as length and width both expand, so then you double the change. Now you might be saying, why isn't it squared? If you're curious, you could look at problem 18.8 on page 66 of volume 3, and I walk you through that and we do the problem. But for now, I just want to mention that areas will expand at twice the rate. And then volumes, 3 times, length times width times height. But this is kind of handy because this would work for a sphere or just a large volume of fluid. And so we typically use this term beta, but beta is just 3 times alpha. Now we're assuming the temperature changes are small enough that they can be modeled as linear changes. I guess in theory, if you heat something up a tremendous amount, then maybe this would become nonlinear and this would only be approximately valid. But for our first approximation, these are pretty darn good for a large number of materials over a large amount of temperature ranges. So we can view expansion as being linear. All right, now there's a table on page 64 with a bunch of coefficients, a bunch of values of alpha. That's in page 64, volume 3. I'm going to provide you some kind of table similar to that on the exam. I'm not expecting you to memorize a bunch of alphas. Let me do it this way. Let me see if I can do this. Sorry, I just don't want to give away the answer. Okay, so let's say we've got a metal plate with a hole in it. The plate is 50 centimeters before you heat it up, and the hole is 39 centimeters in diameter before you heat it up. And I'm going to heat it up so that there's a 10% increase in size of the plate. So I'm going to heat this up until the plate is 55 centimeters. And I want you to think, what do you think is going to happen to the hole? Is the hole going to get bigger or smaller? Now, pause the video and then I'll show you the answer, right? So you can think about it. I'm giving the answer. So again, one time the question. I'm going to heat this up so that the plate increases in size by 10%, even though that's insanely large and unrealistic. This is going to grow to 55 centimeters. What do you think is going to happen to the hole? I'll give you the answer so pause the video if you want to think. Here comes the answer. 3, 2, 1. So after heating, we're going to increase the size of the plate by 10%, which is absurdly large and unrealistic, but easy to draw and show you something. Normally it'd be less than 1%. the hole size also goes up 10%. So the hole doesn't grow by the same amount, it grows by the same percentage. All right, and the hole doesn't shrink. So if you've ever had a metal lid on a jar, a metal lid on a glass jar that's hard to get off, you can run it under hot water. Why does that work? Well, when you heat up the lid, the diameter of the lid increases. Then you may be saying, well, isn't the glass going to also increase? Yes, but the coefficient of linear expansion for metal is larger than it is for glass, so hopefully the lid will expand a little bit more than the glass, just enough to loosen the lid slightly. All right, unusual, there's one very important substance. Water is unusual in this temperature range, 0 to 4C, approximately. So it turns out, as the temperature goes up, in this temperature range only, the volume of water will decrease. So normally when you heat things up, everything grows. The size of the length, the width, the diameter of the hole, everything grows. But with water, between 0 and 4 degrees Celsius, if you heat up water, the volume decreases. That implies alpha is negative for that temperature range only. Consequence, ice will be less dense than water for these regions, right? So the ice will float, and that allows, right, when a lake freezes, the ice is going to form on the top and the fish can live. If you want to go into this more in detail, read a book. I just thought I'd mention that. But for most materials, if we ignore water, this is really what I want you to think about. Ignoring water in this little temperature range, when you heat things up, everything grows. All dimensions grow, including the dimensions of holes. We'll do some problems in a minute, or maybe see some examples in the next video.